So in this session, we would like to demonstrate to you some final year projects done at University of Moratuwa using the robot operating system. So we have been using ROS for some time in projects at Electronic and Telecommunication Engineering Department. And I would like to explain some of these projects together with the other students, my students, the purpose is actually is to give you some motivation to use ROS in your future robotics projects. And when you see these implementations, it will definitely be an inspiration for all of you. And that's our main purpose on demonstrating some of these projects. Then you will feel I can also do this, right? So if this has been done as a project somewhere else, I can also start try to do. Okay, right. So this first project I'm going to explain is called a personal mobility system we developed in 2018. I think you might have seen these kind of systems like Segway robot from Japan. So we wanted to build such a personal mobility system. Now, the system had several sensors. Right. Okay. We have depth sensor, so Microsoft Kinect was used. Then we had RP LiDAR as our 2D LiDAR. Then we had the IMU sensor. So this was the most important sensor in this particular thing because this is a self-balancing robot, right? So the brain of this system was a Raspberry Pi 3. And there was Arduino Mega for motor control, especially the self-balancing aspects and the robot's state estimation. And as for the actuators, we had two brushless hub motors with Hall sensors. And there was a user interface on a smartphone to view the position of this mobility system. And we had several modes in navigation, autonomous mode, teleoperation mode, and also summoning with autonomous navigation. That means, let's say, when your lecture is over, the personal mobility system will come to your door to pick you up, something like that. So let me show you the video of this system. So this was the autonomous mode with a human passenger. So this is the ROS visualization. So you can see a map of the environment. And then here, this is like the interface, just so you can give some commands using that. It's like a joystick we can use to command the system to go to our goal position, right? Then this is like the summoning of the platform. So we can ask it to come to wherever we want, right? So we are using the ROS navigation stack for autonomous navigation. And also in the manual mode with human passenger, you can see the system was able to go nicely on inclined surfaces as well. So this was done in 2020. Let me move on to the next project. So this is called TALRO, or the Terrain Adaptable Legged Robot, built by one of the final year groups, 2019. So we did this in collaboration with our mechanical engineering department, Brandix, and also CSIRO Australia. So our motivation for this project is to come up with a terrain adaptable legged or quadruped robot. So when you say quadruped, that is, it has 4 legs. So it should be able to navigate on different terrain types. And we mainly focused on 3 types, the sand terrain and muddy terrain, and also regular hard surfaces, right? And this locomotion mechanism is called the direct drive 5-bar linkage mechanism, which was kind of a novel technique at that time, because as you can see, we have 2 brushless motors per each leg, right? So unlike we have maybe like servo motors in a like a leg kind of orientation, this is like driven by two like brush motor. So this why it called a direct drive. Right? And the system also had a real sense camera to do the terrain classification and change our moving pattern. We say it as the gait pattern to suit the terrain, right? And as you can see, now this was a new and like unconventional design. So before we even built it, we wanted to test it. So this testing, so this like intensive testing was done on the gazebo simulator, as you can see here, right? And then once we are happy with that, we would move on to the implementation. So on the right-hand side, what you can see is we are like computing the cost of transportation for different configurations. And in the leg, there were some configurations that we tested for the foot. That is like contracted foot, expanded foot. Maybe you have seen these, mountain goats that move on steep hills. So they have different ways of doing it. So with that inspiration, we wanted to test that one. Right. Next, I think Bhanuka can describe this project. So this is his project. So let me give you control. Bhanuka, are you able to?
Yes, Dr. Peshala. Thank you. Hello, everyone. I'm Bhanuka. So this is a project done in 2019 as well, done with collaboration of CSIRO Australia and University of Moratuwa. So this project, in overall, this robot was built up from grounds up, from scratch. It is a leg wheel hybrid robot, and overall, it took less than 1 year for us to build this robot and do all the research associated with that. And everything you can see here is manufactured in Sri Lanka with the laboratories in University of Moratuwa. And for this project, the motivation is so we know, like, if you take wheels, they are very good for energy efficiency as well as for fast travel. So that is why we see all the automobiles in the road, cars, vans, everything, they use wheels, not tracks or legs. One compromise with wheels is they are not good for off-road travel. So if the terrain becomes rough or something like that, the wheels are not that good. So that is where the legged robots shine on their own. So here in this research project, what we are trying to do is whether we can do a hybrid collaboration between legs and wheels and see what are the capabilities as well as how much better energy efficiency we are getting with that. So in this hardware setup, from the left-hand side image, you can see there are 3 wheels. So like we can have like 4 wheels and 4 legs, but it adds to the weight and it is not that good for the efficiency. So we researched and we came up with the solution of having 3 wheels and only 2 legs. So each wheel module, you can see in the bottom, each wheel module can steer on its own and give propulsion. And the legs, you can see from the sides of the robot, we have 3 motors for each leg, and they give the robot to climb over obstacles, as you can see from the right hand side image. Also, we have a camera and a Wi-Fi router to do the communication. The cameras, the purpose of the camera, I'll show in the next slide. So in this right hand side figure, you can see how by generating good trajectories, we can only use 2 legs. We don't need more than 2 legs in this research aspect. That we can clear out many high obstacles and so on. Like we can climb steps, not stairs at the moment, but we can climb over steps and so on. So if I go to the next slide, You can see these are some visualizations we had with our robot. So from the left hand side, you can see that this is what the robot sees. So it is trying to go through this box type of terrain. So it is what the robot is seeing as in the top. So from what the robot sees, we create a digital, what we call as a digital elevation map, or DEM. It is like a 3D representation of the surrounding of the robot. So we have algorithms. So if it is red, okay, the robot might not be able to go through that. If it is blue or yellow, the robot is able to traverse through that using this leg wheel hybrid combination. And so everything in this robot is done using ROS and C++. Sometimes Python for like vision kind of tasks. And in the right hand side, it is a RVis visualization. So why we need a visualization is, yes, we have the robot side by side, but it is better to have a visualization of what are the commands we are giving and whether the robot is following them and so on. So another thing I would like to quickly emphasize is we had a motive, like if we take a wing of a plane, it is modeled after a bird. Like we can get lots of inspiration from the nature itself when it comes to robotics. So here for this hybrid system, we looked at like butterfly stroke swimming, and like if a person is swimming in the water, like we are not using legs anymore, we are using legs and hands as well. Like it is like again a hybrid combination. So here if you can see the motion of the legs with wheels, it is somewhat similar to butterfly strokes swimming, and we name this gait pattern or this trajectory pattern as butterfly stroke, something like how to get inspiration from the nature. Yes, thanks, Dr. Peshala. You can continue.
Right. Oshada, let me give you a control. Do you have control now?
Yeah. For the next project that we'll be talking is the static object detection for self-driving.
Oshada, we can barely hear you. If you can speak a little louder.
Sure. So the next project that we are going to talk about is the static object detection for self-driving, which was done in 2020 as a final year project. And this is focused on one important aspect of a self-driving vehicle, which is the perception. And we are interested in detecting static elements on the road, and that includes traffic signs, traffic lights, lanes, and road markings. So this actually is a little bit different from the other projects that we have showed, because like most of them are robotics related projects, but this one is actually more related to computer vision than actually robotics, because it involves mostly perception. And but the interesting thing is robot operating system could be used, and it's very useful. It was very useful in our project as well. As the detection algorithms, we use three separate deep neural network based networks, one for detecting lanes, one for detecting road markings, and the other for traffic signs and traffic lights. And those algorithms, or those convolutional neural networks are built based on deep learning frames such as PyTorch and TensorFlow. But as to develop this as a complete system, we would need integration, right? Because like in a given frame, we would need to detect all of these elements, and we should visualize them, as well as there will be like other important aspects of a self-driving car which would need these detection results to plan its trajectory and do the rest of its tasks. So that's where ROS came in handy for us. So the integration of these different algorithms is done together with robot operating system. So the detection algorithms, they run as three separate nodes, and the input frame is image message published to these three nodes, and these three nodes will separately detect the lanes, then the road markings, and the traffic signs and traffic lights separately. and their detections are published into ROS topics with the names displayed. And this, like the diagram you are seeing, is the RQT graph of our project. And all those detection message, they have custom message formats specified by us. And as the visualizer, we use ROS visualizer, and that will actually detect. The visualizer node will mark all these detections and show the results on ROS, and as well as like we can the other part of the self-driving car can subscribe to these topics and get these detections for their respective tasks. So let's see a video demonstration in the next slide. Yeah, sorry about that. Back to you, Dr. Peshala.
Thank you, Oshada. We'll move on to the next one. Shalutha, let me give you remote control.
Yeah. Right. So good morning, everyone. So I hope I'm audible. Yeah. So I'm Shalutha. The screen. Right. So this is my final year project done in 2022, which is named as Collaborative Ground Aerial Multi-Robot System for Disaster Response Missions. And this is also a project we done in collaboration with CSIRO Robotics Group in Australia. And we were actually primarily supervised by Dr.Peshala. So first see what we tried to solve using this project. So as we know, aerial robots are optimized for fast exploration with a larger field of view, but they lack and suffer from shorter flight times. And ground robots, on the other hand, they are kind of optimized for longer missions, and they can carry payloads, and they can actively interact with the environment as well if they want. So our primary objective in this project was to use both aerial and ground robot capabilities as a leverage to use in disaster-stricken environments. So considering that, we have designed a drone add-on which can mount to available drones, and designed a head support robot for navigating in uneven terrains while kind of leveraging both of their capabilities. So the high-level system architecture of our solution can be mainly broken down to 3 parts, which is quadcopter, head support, and the ground control station. So in the quadcopter, we can attach our custom designed add-on to it. And then we can perform localization and map creation by using the data coming from the attached IMU and the RGBD camera, which we use as Intel RealSense D435. And the main processing element in our drone add-on was a Jetson Nano. And also while mapping, it can detect victims as well using the implemented YOLO V5 algorithm. And their locations can be seen through the ground control station as well. And on the other hand, the Hexabot robot is actually consists of similar sensors for its localization. And also it is equipped with 2 Jetson Nanos, one used for localization and navigation tasks, and the other one for locomotion tasks. And additionally, we have attached a microphone and a speaker for the teleconferencing with the victim. And also it can carry a payload as well. And finally, ground control station. It is kind of handling all the heavy processing and operation tasks of the whole system, while providing an interface for the operator for real-time monitoring purpose. And if you want to like take manual control, then we can interfere and do. And the architecture you can see here is totally implemented using ROS, and they are implemented as separate nodes, as you can see here, in order to communicate with each other properly to maintain the work. Yeah. So moving on. So basically, if I like summarize what happens in our project is, first, drone equipped with our drone add-on will map an unknown area, and while mapping, it will detect any trapped victims and any other objects and mark their locations on that map. And then that map marked with those locations, victim locations, will be sent to the hex support. And finally, the hex support will autonomously navigate to the target victim locations to deliver medipacks or maybe like perform teleconferencing. And while all these things are happening, ground control station user can see the live video feed. And if he wants, as I mentioned earlier, can manually control the hex support or can interact with the project if he wants. Right. So now I will show you some captured moments in this video. So you can find the full video link, which is published in our ENTC website. Okay, let's see. So this is a drone add-on that we have created. As you can see, it is equipped with the Jetson Nano. And this is a 3D indoor mapping we have done with after creating our add-on. This is a demo environment that we have created. This is a 3D map that we have generated using our add-on. And once we compare it with the blueprint actual map, this is the final result. This is a sample victim detection part that we are demoing here. When a victim is shown, it will mark red. So this is the component diagram of our hex support robot. So localization, it is with the separate Jetson Nano, and for locomotion, it is a separate Jetson Nano. This is just a one gate pattern that we are demoing here, but we have 4 different types of gate patterns. So these are some additional capabilities that we have added into our hex support, so that since this is operating in a disaster environment, those capabilities might be useful for operating in these kind of environments. This is also another additional capability that we have added in our robot. If we want, he can control any legs to manipulate surrounding objects. And this is a demo showing that our hex support is capable of traveling in different kind of terrains without any issues.